Patterns in the noise. In our last video, we asked how advanced alien civilizations might be. But this time we turn it around. Not the great empires, the least advanced visitors, just capable of reaching us. If they are here, could we prove it? Detection is always about information. Patterns hidden in light, radio, heat, or even gravity. The mystery isn't whether they leave a trace, but how faint that trace might be. So what kind of sensor network would it take to notice them, and how long until we get there? Building the baseline. We don't detect visitors by waiting for a single lucky snapshot. We build a baseline, a constant stream of information from countless measurements until we know what normal looks like. An alien ship disrupts that baseline, shifting one pixel, one sensor, one timing channel, a tiny fraction of the whole. We measure that change as a fraction of the baseline pattern. Maybe 1 part in 100, 1 in 1,000,000, or even 1 in 10 to the 20th. As our technology advances, that baseline becomes denser and sharper, mapping our world to finer precision. The smaller the anomaly we can measure, the closer we get to catching what doesn't belong. Detecting a small cloaked ship. Let's imagine a small manned ship visiting Earth. It carries sensitive equipment and crew, so it can't survive high-G maneuvers. Instead, it relies on limited gravity-controlled levitation, moderate speeds, and cloaking to keep its information profile as faint as possible. To catch a visitor like this, we would need to spot a shift of only 1 part in 10 to the 10th, a vanishingly small anomaly hidden in the baseline. For comparison, a stealth fighter alters its background by about 1 part in 100. It would take nearly 100 million of these alien ships to produce the same anomaly as a single stealth fighter. Detecting a tiny hardened drone. Now imagine a different kind of visitor, not a manned ship, but a hardened drone. Unmanned and disposable, built only to scout. These machines can withstand crushing G-forces and dart through our atmosphere at incredible speeds. With no crew to protect, they don't need gravity control, just rugged frames and minimal systems. Their information profile could be as faint as 1 part in 10 to the 20th, 10 billion times harder to spot than the manned ship we first imagined. Drones like these would sweep past as ghosts, leaving only the faintest trace in the baseline. When the world becomes a detector. Our ability to detect tiny anomalies doesn't stand still, it grows. Just like Moore's law in computing, our sensors keep shrinking while our data collection doubles about every 2 years. Imagine a future where trillions of neutral buoyancy nanosensors float through the atmosphere, and trillions of nanosatellites saturate near-Earth space, each one constantly sampling, signaling collisions, and mapping local fields. Together, they build a sharper and sharper baseline until a 1 in 10 to the 10th anomaly, or even a 1 in 10 to the 20th, finally stands out. The denser the network, the sooner ghosts in the baseline become visible. Detected 2145. Our story comes full circle with Moore's law. If detection capacity doubles every 2 years, the climb from a stealth fighter at 1 part in 100 to a manned visitor at 1 part in 10 to the 10th takes about 50 years. Reaching hardened drones at 1 part in 10 to the 20th stretches to more than a century. These numbers are only estimates, but the direction is clear. As our sensor networks grow denser, the ghosts in the baseline will become visible. Join us for part 6, when we put everything together that we have done so far and ask, how do we fit into their plan?